On today's on.net show, we're going to be talking about how you use the actor programming model that comes with Project Coyote to write very reliable async code. Come check it out. Hey, welcome to another episode of the On.net show. Today we've got part 2 of writing reliable async code using Coyote, and we've got Chris again from the Coyote team who's going to, talk about more Coyote things. Thanks for coming by again, Chris.
Hi, Rich. Thanks for giving me another shot here at Coyote.
Yeah, for sure. First, I'm not going to do the whole intro thing again. If people are interested in that, they can watch the first video. So one question that occurred to me while we were actually shooting the other video is, do you use Coyote on Coyote?
That's a great question, Rich. You'd think that we should dog food our own stuff, right? We certainly use Coyote to test our samples, but we don't actually use Coyote to test Coyote. And the reason for that is the internal testing engine is actually serializing everything. There's actually not any parallelism happening inside the Coyote test engine. So it's not very interesting from that perspective that it would need the Coyote test engine to test itself. Although we should do it anyway just to geek out on that, but we probably wouldn't get huge value from it.
Right. So let me test a thought to make sure I get it. Because I would think, like you reiterated multiple times that the coyote.task is just a wrapper on top of system.threading.task. And so my guess is that any case where you can observe a difference between the two tasks, you know what I meant. That would be a bug in Coyote, and so you should never be able to observe a difference.
That's right. Yeah. We actually have, the way we've implemented our unit tests in Coyote is we actually run the wrapper in production mode where it really is just delegating to system threading task. And then we have it running in test mode where it's running more like a mock implementation of system threading task. And those run the exact same set of tests. And so we better get the same output from all of those tests or there's a problem.
Makes sense. Okay, so I think we wanted to talk about something different today.
I did, yeah, thanks. So last time you mentioned, how do people deal with this in other languages and so on. And one thing I neglected to mention is that one popular way for people to deal with concurrency and making sense of parallel programming is to use what's called an actor programming model. And you can see the definition on Wikipedia for actors. And they pop up in lots of different places. And Microsoft also has several different actor programming platforms. One of them is called Orleans. Service Fabric has actors. There's actors in Dapper, which is a new offering from Azure. So actors are super useful paradigm for dealing with async programming. And the way it works is that you don't actually do multi-threading inside of an actor. Instead, each actor can run in parallel, but the internal implementation of the actor is completely single-threaded. It's a little bit like a microcosm of ASP.NET, where every object is serializing all the messages that go to that object. So imagine an actor has an inbox, and all of the messages have to be serialized through that inbox. You can't call an actor from multiple threads. And because when you set it up that way, you've created a beautiful little environment now where the programming inside of the actor is super simple. You never run into parallel problems, and you can call that in a way you can call that a lock-free programming model, because inside your actors you don't need to use locks. So if you remember the bounded buffer example from the previous video, we had to use locks to protect that private state, right? Because we were going to have multiple threads reading and writing, so we had to use locks. And we got ourselves in trouble with a deadlock. So that's a perfect example of why people use the actor programming model to completely avoid that problem altogether. Now, people might also think that you're not going to get the same throughput and same performance out of your system because of this serialization of messages in an inbox. And the truth is that's not so simple. So you can run each actor in a separate task. So the processing of the inbox can be a separate task for every actor. So you can actually end up still with a very, very parallel system. It's just that programming it ends up being a lot easier.
So I too have heard about actors, and I've talked to some of the teams that you mentioned about their actor frameworks, and also .NET actor frameworks like Akka.net from the community.
Yep.
Why do you think they're not more popular? Because it sounds like a great model.
Yeah, I mean, what I'm seeing with our customers in Azure that use Coyote, there's very much two camps. And we have people that are gung-ho on C# async await and absolutely not interested in actors. And then we have other teams that are absolutely all gung-ho about actors. It's a religious thing. I don't think we'll ever see one or the other model take over. I think it's some people really love the actor model, some don't. And so
yeah. Is it a little bit like the functional versus imperative programming language debate?
Yeah, I think that's a good analogy. I think with actors, you have to really understand the value that you're getting from actors, I think, to really fully dive into it. And I actually didn't understand it myself when I first joined the Coyote team. I was like, let's just do async await. That's perfect. And then I wrote this sample. You can actually see it in a Coyote samples of a async coffee machine. So I have this espresso machine at home, and it's a state machine inside that goes through all of these different steps. And I implemented it using async await, and then I implemented it using actors. And at the end of that, I'm like, the actor version is really nice. I sort of started falling in love with actors, so I might be tipping now more to the other side of the the thing. But it's an interesting discussion.
Just means you're open to learning new things.
Oh yes, that's it. Thanks. So anyway, because customers want to be able to choose which of those two models, Coyote actually provides both. And so what I'd like to talk to you today about is the Coyote actor programming model. All right, cool. So over on our website, you'll see that Coyote has two programming models. And last time we talked about asynchronous tasks, which is a thin wrapper on the task programming model. And then you see actors. So actors are provided in the Coyote runtime, and it's a base class. So when you inherit from an actor, you immediately get this inbox behavior. So actors, you can send events to an actor, and that goes through the inbox. And what we do with actors in Coyote is that when you create an actor, you give it the type, and you get back an ID. You never get permission to directly interact with the instance of that type. So client might have methods. You're not allowed to call them. The only thing you can do is you can create an actor, and you can send events to an actor. That's it. An event is just a very, very simple object, which you can see down here. It's also a Coyote base class, but it really contains nothing unless you put some state in there. An event is just, you think of an event as method arguments, bundled up into an object that can live forever in an inbox. It's something that can live outside of a call stack. It's a serialized method call. That's what an event is. And
I guess it's like putting method calls on the heap.
Yeah, exactly. If you could do that, I mean, actually, .NET remoting does do this, right, for serializing method calls across in a distributed system. So you could think of this as a remoted method call, though in our case, it's just living in an inbox in memory. So then what does it look like to implement an actor? So Coyote provides some custom attributes that allow you to do some declarative things with actors. And for example, here I'm telling the Coyote runtime that this actor can receive a ping event. And when that happens, and it's time to process that event out of the inbox, call this method, handle ping. You get the event that was sent to you. I can cast that back to the type ping event. I can then, because the ping event contains an actor ID of the caller, I'm able to use that actor ID to send an event back to the caller. So this is like a ping pong example here, where a server is going to ping, a client is going to ping the server is going to send back another event called a pong event. So this is a very, very, very simple Hello World example of an actor, which actually is a good segue to that Hello World example. Hello World actors. These are all provided on the GitHub where we have Coyote samples, so you can go play with them. The setup is exactly the same. I added a NuGet package, which is Coyote, so it's all just bundled in the same runtime there. And I have a greeter. So if you remember the Hello World last time, I had a greeter object that was doing async methods. This time it's a greeter, but it's an actor. And it gets a request greeting event, and when it gets that event, it sends back to the caller a greeting event containing a random string. And here we're actually using a Coyote random number generator. Remember, the Coyote test tool wants to be able to control random generation, so that's why it's a Coyote method. And it's going to return either hello world or good morning. This example is slightly different from the task-based sample in that we're injecting a different bug here. So what we're going to do is 1 in 10 chance, which is what this means. We're going to send 2 responses to the caller. So we're going to basically send too many greetings back to the caller. And that's the bug that we're injecting here. And so this is now, complete actor. And how do you test an actor? Well, typically what people do to test actors is they create a sort of a test actor, which is the thing that's going to fire off what it is that you're testing. So the test actor has all actors have an initialize method, and I'm going to create the greeter, and I'm going to iterate a certain number of times, sending a greeting request. So up to 5, random number 5 here. So it'll send 1 to 5 greeting request events. It'll keep a count of those in memory here. And then it's told Coyote with a custom attribute that it's expecting a greeting event to come back. And when that happens, call this method handle greeting. All right, down here is our handle greeting, where we decrement the count and we print out what we received. Now we can do an assert. So here it's asserting that count never goes negative. But remember, we injected a 1 in 10 chance that will actually send too many greetings, which will make it go negative, and we should hit that assert. All right, so this is now our hello world greeting example. And how do you fire off this test actor? So the way you create a test method, the same way we did before with the systematic testing test attribute, that'll tell Coyote this is the entry point for the test. Now, instead of a Coyote runtime, we use the actor runtime. Actor runtime lets us create actors, which is what we're going to do. We're going to create the test actor. Now, this will all run completely asynchronously, right? And so all these actors, in fact, in Coyote, each actor does run in its own task. So the other thing we do to fire off this thing outside of Coyote test, if we want to run this program in production, not inside the test engine, then we also need to create that runtime. So we create what's called a production runtime, and we call the execute method with that runtime. Now, all of those actors, the test actor and the greeting actor, are all running in parallel in separate threads. So this program needs to just block with a read line to stop it from terminating. So I'll go ahead and run that. And then when I run the production version of this, we see the output. Requested 2 greetings, received 2 greetings back, and everything just ran fine. So it didn't hit the assert. All right, so that's how, and then of course it blocks because I've got that read line, so I can now terminate. All right, so that's how you run a Coyote actor program. And how do you test it? Well, you test it exactly the same way. I'm going to run Coyote test, and this time I'm going to run hello world actors.dll, and I'll run 100 iterations. Now, there's interleavings to test here. There's what happens, because each act is running in parallel, it can test different orderings of messages. And if you remember the raft example that I showed before, which looks like these are all actually actors. These are actually running in parallel, and in production, they're gonna run like this. Right, so all of those messages happening in parallel, Coyote can actually test that. So this test finished, it found a bug, and just as before, we get a log file. Now, in the actor programming model, the log file also contains every message that was queued and dequeued and so on. So you get, and every send event call and so on is logged. So you get a lot more logging output, but the bug happened, too many greetings returned, shows you where that is, and it provides the schedule that allows you to reproduce that bug exactly. Make sense?
It does. So this question probably doesn't matter, but is the Coyote implementation, like the test part of it, completely distinct from the task one that you showed us in the first video, or is it kind of just a wrapper in the sense that you said that the actors are built on top of tasks, I think, or something like that?
Actors do use tasks, and the Coyote test engine has a core test engine that is actually the same across actors and tasks. We basically map everything to what we call internally an async operation. And anytime there's a scheduling decision to be made, it's just choosing between a list of enabled async operations. And so it's actually a much more abstract inside the Coyote test engine. So it can deal with both of these programming models basically the same way.
One more question on that, which is we were obviously talking about the Coyote actor model, but earlier we said that there's a bunch of other actor models. So for example, if the Orleans team or the Service Fabric team wanted to enable Coyote with their actor model, what would that look like?
That's a great question, and we've actually been having those discussions. There's two ways. So Orleans has the concept of grains, and grains are an actor, and Orleans does this incredible magic for you to distribute those grains across silos and automatic load balancing and so on, and all of that magic is what you get with Orleans. But the implementation inside of a grain could actually use these Coyote actors if you wanted to. So that would be layering inside of Orleans. Orleans wouldn't necessarily know that you're using Coyote to implement your grain. The same thing can be done with Service Fabric, where it's just an implementation detail. Just like if you choose to use a task-based, programming model inside a grain, Orleans doesn't care. That's fine. You're just using a C# library. Same thing is true with Coyote. You can just choose to use it as a library. Now, what could be more interesting is to have Orleans, the full distributed system that you build with Orleans, to have Coyote know about the Coyote test engine, know about that distributed system and all the different grains and how they're communicating with each other and test that. Now that would require a much deeper integration between Coyote and Orleans potentially, and what we're trying to think about is whether we can expose this core test engine with the async operations as something that other people can plug into. And that would potentially enable people to leverage the systematic testing that we're doing in other environments. But that would take work.
Yes.
So in what I mentioned before is that Coyote has these different scheduling algorithms, and the one that it uses by default is just a very simple random scheduler. But it gets more interesting when you can use probabilistic. There's a PTC scheduling strategy, and all of these have various research papers written about what these strategies do. And one of the things that I didn't show last time is that you can actually tell Coyote to test your program with different scheduling algorithms, and that's what portfolio means. And so I'm going to do that here. I'm actually going to say test this program with different scheduling portfolios. What that means is different ways of exploring that state space of different interleavings. And the other thing we can do with Coyote is we can actually run multiple processes. So it'll run 5 parallel processes all exploring this program with different scheduling algorithms. And you can see here it actually launched all of those in parallel. And those tasks are now running, and it's exploring and finding that bug. So when you've got those really, really hard bugs to find, this can be a really great way to fully utilize the power of your machine to explore all the possibilities and get more coverage more quickly. Speaking of coverage, you can actually ask for a coverage report of actors, and I'll ask for activity report. So what that will do is it'll produce a coverage report that looks like this, that'll tell you what events were sent, what events were received in your actors. And you can look at that coverage report and figure out if your test is actually missing stuff. And we also produce, one of my favorite things, is a way to actually visualize that using DGML. So this is now a picture of what happened during that test. Now we have a more interesting example. The Hello World one is pretty trivial, but we have one here that's implementing a state machine and is doing a failover test of a state machine. So this coffee machine, it's my favorite coffee machine. It just works and works and works. And it has a little state machine. So what does it do? It checks the sensors, it heats the water, it when the water's ready, you can make a coffee, it starts grinding the beans, it makes the shots, etc. Then it cleans up, dumps the grinds, etc. There could be some error conditions that happen along the way. And so this is now actually a full state machine. Now you can implement a state machine in Coyote because Coyote actually has a first-class state machine type and a way of declaring state machines in a more declarative way. So in C#, you can write a state machine with just some private members. I might have a member variable called state that might be an enum that has these values, right? But with Coyote, you can actually lift that up and make it more declarative. And the advantage of doing that is that Coyote can actually explore that state machine. And so I'll show you what that looks like in code. So coffee machine, actors. And here's the diagram, same state machine that's being implemented. And the coffee machine class is, if I scroll to the top, a state machine. This state machine type is a subclass of actor. So this is actually what Coyote started with. We actually only had state machines originally, and then we realized that there's this sort of base class for state machines called actor. Because the state machine also has an inbox. It had many of the same properties of an actor. It's just that it has more. It has this concept of states. And so you'll see in the state machine where I declare a state. So a state is a Coyote state machine type. And I can say there's an init state. This is actually the start state for the state machine. What I can call a method when I enter that state. I can also do advanced things like tell it not to process this event. So actually, you can actually stop the inbox for a little while until you're ready, and that sort of thing. It's pretty advanced. And then down here, I have a check sensor state. These are all, check sensor was one of the bubbles in that diagram. So I have a check sensor state, and I can declare all the things that can happen in that state. So with actors, all of these declarations were at the class level, but in state machines, they can be at the state level. So you can actually have a finer grained state machine that says, I'm only expecting these events when I'm in this state. When I'm in other states, it would actually be an error to get those events. And so on and so forth. So now I've declared this full state machine. And what this program does then is it implements that coffee machine. And when I run it in the debugger, you'll just see a bunch of command line output as the program runs. And the coffee machine warms up the water, it grinds the coffee, it pours the shots, and it goes off, and it just keeps on running. Now, this is cool. This implements a state machine, and it's looking for problems. But the interesting thing about this test is it does one thing extra. So in the cloud space, it's really important to do what's called failover testing. And when you have microservices all talking to each other, you need to be able to handle what happens if that one of those services dies and comes back again later. And you want to actually systematically test that failover condition. And so that's what the sample is all about. What we're doing is we're basically imagine we're rebooting the coffee machine. The little CPU inside that coffee machine, it's probably some embedded computer in there, glitches out and reboots. And what this test is looking for is when that thing reboots, is the second coffee machine instance going to do something bad when it comes back up? So those are the kinds of bugs we're looking for. We're basically hardening the firmware, if you like, to make sure that it's never going to do something stupid when it runs into an error like this. Or the user can also just hit the power switch at any point, right? The user can just power off the coffee machine, power it up, and this makes sure that it's not going to do something silly. And what we've done is we've set up a failover test driver that will actually randomly halt one of the coffee machine instances and create a new one. Of course, the sensors on the machine that tell you how much water, what the water temperature is, how much coffee you have, all of those sensors stick around. So those live for the whole. We don't reboot those. Those live for the whole life of the test. We're just going to reboot the coffee machine. So with this failover test, then we actually have some asserts in the code. So we're going to assert some things like never turn on the water heater if there's no water. Don't turn on the grinder if there's no beans in the coffee machine, and so on. So these are safety asserts, if you like, to make sure the machine doesn't do something silly. If somebody opens the door, make sure we don't, jam their fingers in the coffee machine, right? So make sure the coffee machine does not run if the door is open. So these are all safety type of things that you'd imagine that you'd want to have in this code. Now we can test this coffee machine the same way as we tested all the other stuff. And I'm going to test coffee machine actors. And I'm going to run 100 iterations. And this is now going to run systematic testing. So instead of the command line test that you saw, where I was just running it from the command line, that was production run. This is a test run. And this is the one that's going to do the failover testing. It's going to kill the coffee machine and restart the coffee machine and look for bad situations. And indeed, it found a bug already. And remember I said we get a lot more logging output. These are all the messages that were sent and received. So when you create big distributed systems that are doing a lot of different messages all over the place, you can get a lot of activity. And these are the kind of logs that people have to plow through, right, to figure out what happened in a real system. And here it found the assert, don't turn on the grind if there's no beans. So somehow when it rebooted that coffee machine, it went straight through and started grinding beans when the hopper was empty, which triggered the assert. So there is a bug in the code. We actually injected a bug in the code on purpose, but it shows you that some of these bugs can be hard to find. It ran 600 operations before it found that bug. But again, you can reproduce it 100% with that schedule, just as before. So if I run replay, I can just do that. And replay. Schedule. Schedule, not text. Right. And of course, you get the 100% reproducible replay here. No matter that, even though all of those different state machines and actors are running in parallel, this replay is still 100% guaranteed. Now, that's only 100% guaranteed because Coyote has captured what we call all types of non-determinism. And there's a whole section here of non-determinism. That's what Coyote is really all about, is capturing and controlling non-determinism. And so you have to be careful and make sure that Coyote is aware of all your non-determinism. For example, if you use random number generation and you don't tell Coyote, then you may have non-determinism that Coyote doesn't know about. And then you'll lose that guarantee of 100% reproducibility.
So that all makes sense to me. One of the things that was going through my mind as I was listening to that is, it's like, I really appreciate the safety that you're bringing to me, and I totally believe everything you said. But some of these layers seem relatively thick in nature. So can you speak to me about any performance trade-offs that exist?
Sure. So yeah, if you ran an actor or a state machine, and did a local on your box throughput comparison between that and the task-based version, we actually have a task-based version of this coffee machine as well, coffee machine task and actors, and you can do that. You could actually do a performance test to compare them. You will see that the inbox has some overhead, and the fact that I have to new up an object called an event instead of just calling a method obviously has overhead. So there will be a cost to using the active programming model. Our customers in Azure that are doing this, their actors are doing HTTP requests, right? So when you compare the cost of a state machine to the cost of an HTTP request, it's negligible. So you're not going to see that. The other thing that some of our customers are reporting is that because actors give you this lock-free, completely single-threaded programming model, you just don't have to worry about multi-threading. They're actually more confident about using actors, which means that they can create more actors.
I see.
And therefore get more parallelism in their system as a result, and get better throughput in the end. So they actually see that one of the customers ported their stuff over to this, and actually at the end of the day, they were reporting higher throughput numbers on their overall service. So that's anecdotal. It's not proof or anything. Yes, on a very small fine-grained test, you'll see the overhead of that, newing up events on the heap and an inbox and so on. But in the big scheme of things, you might actually see a design that's easier to understand, easier to visualize, and easier to debug. So you get all of these maintainability benefits, and potentially even better throughput in your system at the end of the day.
Yeah, that actually reminds me of where we started the very first video, which is, is async bad since it has all of these potential reliability problems? And what I hear you saying is, when you go all the way to this actor model, it could actually completely unlock your ambitions with respect to exploiting asynchrony.
Yeah, I think that's a great way to put it. Async is not bad. Locking is bad because you can end up with a lot of contention on those locks. And if you've worked in any system level programming, it'll be the bane of your existence to minimize the contention on locks, right? Whereas with active programming model, you don't have to do that. Obviously, you're depending on the Coyote runtime implementation of actors, where we do have to use locks to protect the inbox. So you're hoping that we've done a good implementation of the active programming model, and hopefully we have done a good implementation. We're actually always tweaking it and improving it, and so on for our customers in Azure. So, that's where you take a dependency on something, you're gonna depend on that. On us to get that right. However, this is a good plug for our GitHub. It is all open source. Coyote is up here. You're welcome to come look at it, play with it, hang out, file issues, file pull requests. You can see our runtime in here with our active programming model. You can see actors here and so on. So you can actually see how we've implemented actors. And if you're not happy, help us fix it.
For sure. So one question, which is, imagine I'm in the multi-threaded audience that we talked about before, and I haven't adopted tasks, but I have all the problems that you kind of outlined. What would be your suggestion to me?
Well, I think Coyote provides two programming models, because we are not in the game of forcing you to use one or the other. So we recommend use the programming model that makes sense for you. If you're already using tasks, then please start with Coyote tasks. Don't try to jump to actors. We're not going to force you to jump to actors. Only when you run into we think that there's sort of a complexity ceiling that you run into with tasks. Only if you're pulling your hair out and running into contention on locks, and you're just really having a hard time with task programming, then please explore the active programming model, and especially the state. We're super happy with the state machine concept that we have in here as well, in terms of surfacing that up and making it something that you can visualize. It helps you with the design of your programs to actually see what's happening in all of your states. So this we think of actors as a more advanced programming model. We think of it as something that that you should use if you're building really complex distributed systems, and it will help you reason about those systems, design them, and understand what they're doing.
That makes sense. Really what I meant is, if I'm still in the world of using threads directly, but I loved everything I heard here. I think the guidance, please correct me, is that you should adopt tasks as your kind of concurrency substrate, like, and then you can use Coyote, but you at least have to switch to tasks.
Yes, that's right. You won't get any benefit from Coyote until you switch to the Coyote task type.
Yeah.
That's right, which is this one here. And then you'll get benefit from the Coyote test engine. Yeah, I would certainly start there. I think most people do start with the task program model, and they only switch to actors when they're really desperate and they're looking for something more advanced, more sophisticated.
Okay, awesome. Well, I think this was an amazing two-part series. Any closing, calls to action or thoughts you want to share before we close out?
Yeah, absolutely. Thanks, Rich. Only to point out again that it's open source. We really want people to contribute. We've got the GitHub here. We really want people to file issues there, and we hang out on Gitter. So go check out the discussions we have there. We'll answer questions quickly, and yeah, we're really looking forward to getting the word out there and getting community participation.
Awesome. Well, thanks for spending so much time with us, Chris. This is the second in a two-part series on how to write reliable async code with Coyote and .NET.